Below the link to this video, you will see a link that takes you to a video of Commander David Scott dropping a feather and a hammer on the surface of the moon in 1971. The idea was that he was demonstrating that all objects fall at the same rate in a vacuum, that only the gravity of the situation is what matters. If you look up the acceleration due to gravity on the moon, you will find that objects fall at about minus 1.6 meters per second squared on the moon. That's about 1/6 of the gravity, acceleration due to gravity on Earth. Well, if I think about it, that means on the moon, the acceleration function is constant. Minus 1.6 meter per second squared. Well, what I know about acceleration is that acceleration is the derivative of velocity. So what I really have there is a statement about a derivative. If I wanted to know a velocity equation for objects dropped on the moon, well, I'm looking for a function so that that's its derivative. The second corollary to the mean value theorem says that if two functions have the same derivative, then they differ by at most a constant. So if I write down a possible function that has this derivative, the actual velocity equation I'm looking for might differ from it by at most a constant. Well, I'm looking for a function whose derivative is minus 1.6. Give yourself a second to see if you can guess a function that would have that derivative. When I think about functions whose derivatives are a constant, I think about lines, so minus 1.6 times t. Now, I don't know that this is the actual velocity equation. The one I'm looking for might differ by some constant, that constant coming from the second corollary to the mean value theorem. All right, so v of t equals minus 1.6 t plus c. All right, well, now I want to see if I can figure out what that value of c is. If you've watched the video clip of David Scott dropping the hammer and feather on the moon, what you see is that the hammer and feather start off in his hand. And so at the instant he drops them, right before they even start to fall, the velocity is 0. So I would claim that gives us an initial velocity. That the velocity at time 0, when the hammer and feather are still in his hands, the velocity is 0 meters per second. And that'll actually give me enough information to figure out what c is, because v of 0 is also equal to minus 1.6 times 0 plus c. Well, if that has to be 0 meters per second, then c has to be 0. Well, with that, I know the true velocity equation is minus 1.6 t. So, the velocity of the hammer and feather as they fall on the moon obey this equation. You plug in a value for time in seconds and you get out the velocity of the hammer. Now let's say I wanted to find an equation for position. Well, what I remember about velocity is that velocity is a derivative of position. So I'm looking for some function that has this derivative. Well, again, all of the functions with this derivative differ by at most a constant. So if I find one potential function that has this as a derivative, then I should be able to find the exact one I was looking for because it may differ from what I write down by some constant. All right, well, again, take a second and see if you can guess a function that has this as its derivative. Okay, when I think about functions whose derivatives are t to the first, I think I need a t squared. And just imagine working backwards. If I take a derivative, I would have 2 times t to the first. Well, I need 2 times something to be equal to minus 1.6, so I'm going to say that's a minus 0.8 plus some constant, because all of the functions with this derivative differ by at most a constant. I'm not going to call my constant c, because c is equal to 0. It doesn't stand for an arbitrary constant anymore. I've said that c is 0, so I'll call this constant k just to use a different variable. All right, well, I actually want to figure out what k was. And if you've watched the video and read the caption beneath it, NASA is telling me that Commander Scott dropped the hammer and feather from about 1.6 meters above the lunar surface. So at time 0, when both the feather and hammer are in David Scott's hands, we're 1.6 meters above the lunar surface. So I have an initial position. Well, S sub 0 is also minus 0.8 times the time squared plus k. So S sub 0 is both 1.6 and the value of k. So k has to be about 1.6. So just knowing the acceleration due to gravity on the moon, how fast Commander Scott started, how fast the hammer and feather fell initially, and an initial position, I was able to find both a velocity function and a position function for the hammer and feather as they fell on the surface of the moon.